This is Dr. Shankaraiah from Department of Physics. So, in this presentation, I am going to discuss about laser and fiber optics, and basically on fiber optics, numerical problems on these fiber optics. So, I've completed all the theoretical part of the fiber optics. Okay, starting with the principle and construction, and then classification of optical fibers, and then propagation of light signal through different optical fibers, and block diagram of optical fibers, applications of optical fibers, losses and losses in optical fibers, advantages, disadvantages, and all these theoretical topics I've covered in earlier presentations. And in this presentation, I'm going to discuss about numerical problems on optical fibers. So the first problem is that a strip index fiber has a numerical aperture of 0.16 and core refractive index of 1.45. Estimate the acceptance angle of the fiber and refractive index of the cladding. So they have given that a strip index fiber has a numerical aperture of 0.16. So they have given numerical aperture which is 0.16 and core refractive index is 1.4. So using these inputs, okay, so given as mentioned here, they have given numerical aperture which is 0.16 and refractive index of core which is N1 is 1.45. Now we have to estimate acceptance angle, right? Theta A, and refractive index of the cladding which is N2. So we have to calculate these two. So always we need to start with the given, whatever inputs they have given, we have to start with those. So numerical aperture is given of this optical fiber and the refractive index of the core is given. Okay. So we need to find the refractive index of the cladding and the acceptance angle. Okay. So the formula for acceptance angle, we know that acceptance angle formula theta A is sine inverse square root n1 square minus n2 square by n0. We have derived this formula, acceptance formula, which is sine inverse square root. Okay. So sine inverse square root n1 square minus n2 square by n0. So there is no square root for n0. Okay. So where n1 is the refractive index of core and n2 is refractive index of cladding and n0 is the refractive index of launching medium. Okay, so N0 is refractive index of launching medium. We are launching the light into the fiber, right? So whatever the launching medium we are considering, the refractive index of that launching medium is N0. If we are taking the launching medium as air, so N0 refractive index for air is 1. So that is why I can write down this formula simply as sine theta A. Simply I can write, if I take air as a launching medium, sine inverse square root n1 square minus n2 square. Okay, so sine inverse square root, we know that the formula for numerical aperture is square root n1 square minus n2 square by n0, but n0 is 1 because we are taking the launching medium as air. So numerical aperture is square root n1 square minus n2 square. So basically whatever we have in this bracket is numerical aperture. So acceptance angle is sine inverse numerical aperture. So they have given the numerical aperture. So substitute this numerical aperture value. So sine inverse of 0.16, which is 9.206 degrees. Okay. So now we have calculated the acceptance angle for this fiber with a numerical aperture of 0.16. Now we need to calculate the refractive index of the cladding because they have given only the refractive index of the core and numerical aperture value. So without knowing the refractive index of the cladding, we have calculated acceptance angle because they have given us numerical aperture. Okay, so that we have directly substituted in the formula and we got the acceptance angle. And the numerical aperture is defined as square root n1 square minus n2 square by n0, but n0 we have taken it as a1 because we are taking launching medium as a. Okay, so from this formula I am going to squaring on both sides. Squaring on both sides. Squaring on both sides, what happens to this formula? Na square, numerical aperture square, is equal to n1 square minus n2 square. Okay, so I want the numerical aperture of cladding. Okay, so then numerical aperture of cladding n2 square is equal, I'm going to take this side, so n1 square, n2 square is equal to n1 square minus numerical aperture square. Okay. So our n2 is equal to square root n1 square minus na square. So substitute the value of core refractive index. N1 is the refractive index of core. They have given it as 1.45. So 1.45 square, and numerical aperture they have given as 0.16. So square. So substitute the values of N1 and numerical aperture. We are going to get the numerical refractive index of cladding as 1.4. Okay. So in this formula we have calculated acceptance angle of a given fiber and refractive index of cladding. Okay. So this is what we have done. We have calculated the acceptance angle and refractive index of the cladding using the inputs of numerical aperture and refractive index of the core. So let us go to the next problem. So all these equations, numerical aperture equation and acceptance angle equation, we have derived in the earlier presentation. Okay, so you can go back and look at the presentations for the derivations. Okay, so the second problem is that the refractive indices of the core and cladding, materials of a step index fiber are 1.48 and 1.45 respectively. Simulate numerical aperture as well as acceptance angle. Okay, given they have given the refractive indices of core and cladding. So refractive index of core is N1, which is 4.48, and refractive index of cladding is N2, which is 1.45. Okay, using this we need to calculate numerical aperture. We know that numerical aperture formula is n1 square minus n2 square by n0. But in general, we take n0 as air. So n0 is equal to 1. So that is square root n1 square minus n2 square. So substitute the values of n1 and n2. n1 is 1.48 square minus 1.45 square. So numerical aperture is 0.2965. Okay. So with these values of core and cladding refractive indices, we have calculated the numerical aperture, and we can calculate the acceptance angle. Acceptance angle is theta A, that is sine inverse square root n1 square minus n2 square by n0. So anyway, we have calculated numerical aperture. So you just substitute sine inverse of 0.2965, you will get the acceptance angle of this fiber. Okay. So if you know these two formulas of numerical aperture and acceptance angle, it is very easy to calculate for the given input values of refractive indices. Okay, so I've used the acceptance angle formula. Sine inverse square root n1 square minus n2 square are nothing but numerical aperture. Okay, so yeah, so you can directly write like that, or you can directly write sine inverse of numerical aperture, and that is 1 anyway. So sine inverse of 0.2965. So you will get 17 degrees 15 minutes as the acceptance angle. Okay. Yeah. So we have calculated the numerical aperture and acceptance angle of a given fiber with the inputs given as refractive indices of core and cladding. Okay. So this is the second problem. So third one is an optical fiber has a numerical aperture of 0.2 and a cladding refractive index of 1.59. Optical fiber has a numerical aperture of 0.2 and cladding refractive index is 1.59. Find the acceptance angle for the fiber in water which has a refractive index of 1.33. So now, they have given numerical aperture. So given, always start with a given input parameter so that it is easy to use them in the calculation. So given is numerical aperture, which is 0.2, and the refractive index of cladding, which is N2, which is 1.59. Okay. So now they have asked us to calculate the acceptance angle of the fiber in water. So now acceptance angle formula theta A is sine inverse square root n1 square minus n2 square by n0. our numerical aperture, or you can write like this. Okay, so square root n1 square minus n2 square by n naught. Okay, now n naught is the refractive index of the launching medium. Refractive index of launching medium. Okay, so if you take air as the launching medium, then refractive index of air is 1, so you don't need to take n naught, it is automatically 1. But now they have given the launching medium is water, so now you have to substitute the refractive index of the launching medium, which is water, so that is 1.33. Okay, so square root n1 square minus n2 square is numerical aperture, which they have given as 0.2. So substitute the value of numerical aperture with air as launching medium. So you are going to take numerical aperture as 1.59. Okay, so we need to calculate the acceptance angle in water, right? Yeah, so acceptance angle formula is sine inverse numerical aperture by n naught. So numerical aperture, we have square root n1 square minus n2 square by n naught, but they are given numerical aperture is 0.2, and the launching medium n naught, refractive index of the launching medium, is n naught, which is equal to 1.33. So substitute the values of square root n1 square minus n2 square, which is numerical aperture. Okay, and then if you are taking air as launching zone, then the numerical aperture is square root n1 square minus n2 square directly. But here you are taking the water as launching zone, so substitute this as numerical aperture, and then n naught as the numerical refractive index of the launching zone. So when you substitute all these values, you are going to So this is So this one is sine inverse. This is not correct. Sine inverse 0.1504. So sine inverse of this value is 8.65 degrees. Okay, so this is the acceptance angle of the fiber. Acceptance angle of the fiber with the given values of numerical aperture and the refractive index of the launching medium, which is water. Okay. So we have calculated the acceptance angle of a fiber considering the launching medium as water. So now calculate the fractional index change for a given optical fiber if the refractive indices of the core and the cladding are 1.563 and 1.498 respectively. Okay, so now they have given refractive indices of the core and cladding. Okay, so refractive index of the core is N1, which is 1.563, and refractive index of the cladding, which is N2, which is 1.498. Now they have asked us to calculate the fractional refractive index, delta. Okay, so delta is fractional index change or fractional refractive index change. We need to calculate this. So the formula for the fractional refractive index change is N1 minus N2 by N1. So we have also, in deriving the numerical aperture in terms of delta, we have defined the delta as N1 minus N2 by N1, right? So substitute the values of N1 and N2. N1 value they have given as 1.563 minus N2 value they have given as 1.498 divided by 1.498. So we will get the answer. Fractional refractive index answer is 0.0416. Okay. So this is another kind of problem which we have solved, calculating the fractional refractive index of a given fiber with the inputs given as refractive indices of the core and cladding. So this is another kind of formula. Up to now we have used only numerical aperture and acceptance angle, but now in this problem we have learned there is another formula which is for fractional refractive index change. Okay. So the fifth one in this optical fibers, the problem is the mean optical power launched into 8 kilometer length of fiber is 120 microwatts. Okay, the mean optical power launched into 8 kilometer length of fiber is 120 microwatts. The mean optical power at the fiber output is 3 microwatts. Find the overall signal attenuation and signal attenuation per kilometer. Okay. Now they are saying that you have an optical fiber, so we are launching the light signal into this optical fiber of length 8 kilometers. So given, so length of the fiber, let us say length of the fiber is L, length of the fiber L is equal to 8 kilometers, 8 kilometers. Okay. Then input power, the mean optical power that is launched into the, so input power Pi is equal to 120 microwatts. So you convert into watts, 120 into 10 power minus 6 watts. And the mean optical power at the fiber output. So the output power that you are going to receive at the output end is 3 microwatts, which is 3 into 10 power minus 6 watts. Okay, so we have discussed about this attenuation and distortion of this optical signal through fiber, and the formula for attenuation coefficient alpha decibel in terms of decibels per kilometer, in units of decibels per kilometer, is 10 by L log 10 Pi by Po. Okay, so now we are going to substitute these values of Pi 10 by L. So 10 by L is what? L is 8 kilometers. And log 10, Pi is what? Pi is 120 into 10 power minus 6 divided by 3 into 10 power minus 6. Okay. Substitute these values. We are going to get the attenuation over all length. Over the length of the fiber is 8 kilometers. The attenuation of the signal at the distance of 8 kilometers, we are going to get. Okay, so the attenuation of the signal is 10 by L log 10 Pi by Po in units of decibels per kilometer, right? It's very important. Then, so now we want to calculate over all length, right? First, they have asked us to calculate the attenuation, overall attenuation, and then signal attenuation per kilometer. To calculate the overall attenuation, overall signal attenuation. Overall signal attenuation is alpha decibels per kilometer into L is equal to 10 log 10. This is not natural logarithm, it is log 10 Pi by Po. So input power divided by output power. Okay, so this is the signal attenuation for overall length. Okay, so that is 10 log 10 Pi is 120 into 10 power minus 6 watts. This is 3 into 10 power minus 6 watts. So 6. 10 power minus 6, 10 power minus 6 will cancel out. So 10 log 10, 120 by 30. So this is 4. Right? So 40. So the answer is 16 decibels. Okay. So alpha decibels per kilometer into L over all length. Over the overall signal at 8 kilometers length is 16 decibels. Now, this is the first one. Overall signal attenuation is 16 decibels. Now, second one is signal attenuation per kilometer. Okay. So, alpha decibels per kilometer is, now you are going to take this L to this side. So, that is 16 decibels by L. What is the length of the fiber? Length of the fiber is 8 kilometers. So, that is basically 2 kilometers, 2 decibels. So that is 2 decibels. So the overall signal attenuation of this fiber of 8 kilometers is 16 decibels, and the signal attenuation per kilometer is around 2 decibels. Okay. So we have calculated the signal attenuation, overall signal attenution over the length of the fiber, and then signal attenuation per kilometer in this problem. So I will revise these ones. Yeah. So to summarize, we have discussed numerical problems on optical fibers. So starting with first, we have calculated the acceptance angle. We have calculated the acceptance angle given numerical aperture and refractive index of core. Okay. So in the second problem, we also calculated the numerical aperture and acceptance angle. Acceptance angle given refractive index of core and refractive index of cladding. Right? And then in the third problem, again, we have calculated the numerical aperture and acceptance angle. But here they have given the launching medium refractive index, which is 1.33, and the medium is water. Even though the formula is same, in general we are going to take air as launching medium, so we take n naught. Refractive index of air is 1, so we take n naught as 1. But in one of the problem we have discussed that launching medium is not air, it is the water, so we have substituted the value of n naught as 1.3. Okay, so then in the fourth problem we have discussed fractional refractive index change. Fractional refractive index change, that is delta, which is we have calculated this given refractive index of core and clarity. Finally, we have calculated the attenuation of signal. Okay, so to calculate all these acceptance angle, numerical aperture, and fractional refractive index and attenuation of the signal, we have used four different formulas. Okay, so formulas to note to solve the problems in optical fibers, starting first with numerical aperture. So numerical aperture is defined as n1 square square root n1 square minus n2 square by n naught. So generally n naught is launching medium, so this is launching medium refractive index. It is air, mostly it is air, so we generally take refractive index numerical aperture as square root n1 square minus n2 square. So this is the formula we use. Okay, so that is the formula for numerical aperture. Then the formula for acceptance angle. Formula for acceptance angle is sine inverse square root n1 square minus n2 square by n naught. Even in this formula also, if they have not mentioned the launching medium, then we are going to take launching medium as air, and then we are going to use the formula sine inverse square root n1 square minus n2 square. Because if they have not mentioned the launching medium, we are going to consider as air is the launching medium and the refractive index of air is 1. So n naught is 1. We are going to use this one. So the third formula which we need to learn or we need to use is fractional refractive index change delta, which is n1 minus n2 by n1, where n1 and n2 are refractive indices of core and clarity. So this is the third one. And the fourth formula we have used in this in solving these problems is that attenuation coefficient, which is alpha, in the units of decibels per kilometers, that is 10 by L log 10 pi input power by output power. So these are the four formulas which we have used in solving the different numerical problems on optical fibers. Okay, so we have also in earlier presentations I've also discussed about derivations of these formulas, right? How did we get this numerical aperture and formula square root n1 square minus n2 square by n naught. I've also derived this formula for acceptance angle, which is theta a is square root sine inverse square root n1 square minus n2 square by n naught. And I also used this fractional refractive index. I have defined fractional refractive index delta as n1 minus n2 by n1 when we are deriving the equation for numerical aperture. And then this attenuation coefficient, I have discussed about attenuation and distortion, and I have also derived this formula for attenuation coefficient using that the signal strength decays exponentially with distance. Okay, so with these five problems on optical fibers, so we have completed the third module of lasers and fiber optics. In the next presentation, I will discuss about next module.
Like, share and subscribe. Hit the bell icon for more updates.